All right, welcome, chemists. We are going to start with, on your notes packet, it should say page 7, chapter 5, molecule 7 of 13, and it should say things you should know. And it should be, wow, I have a lot more to do in that other block. All right, so your top left slide should look like this. Things you should know from the story of Chem. Chapter 5, section 2, number 1. If two atoms sharing electrons in a covalent bond have very different strengths, and by strengths, we really mean somebody shout out a color. I heard blue first. Blue. All right. When we talk about the strength of an atom, what are we really talking about? There's a word there. Yeah, Eli. Electronegativity. And if you ask Mr. Hamill sometime about his greatest bananagrams moment, it was starting out with electronegativity as his central word. It was pretty glorious. All right. The electrons are not shared equally if they have different electronegativities. So one end becomes partially positive and the other end becomes partially negative. We call these bonds polar. Now this probably is something that rings a bell. Each pair of electrons around an atom wants to be as far apart from the others as possible. So we know that single electrons want to be as far away from each other, but we're going to be thinking in terms of pairs, and with the word, that key idea of repulsion. Go back to our fundamentals, right? Coulomb's law, we can talk about the strength of attraction and repulsion, and we know that like charges repel. Molecules have different shapes based on the number of valence electron pairs around the central atom. So really what we're going to be talking about in this section is molecular shape and molecular polarity and bond polarity. All right, two more things you should know. These are objectives, right? So if the partial charges in a molecule are asymmetrically arranged, what does asymmetrically mean? Nathan? Not equal. Yep. We're giving you your SAT practice. Asymmetrically arranged, then the molecule is considered polar because it has a positive pole and a negative pole. Just like our Earth has the North Pole and the South Pole, molecules can have a positive pole and a negative pole. If the partial charges are symmetrically the same around the nucleus, or if there are no partial charges, then it's nonpolar. Now this one is really interesting, especially for those of you who are going to go into biochemistry at some point in your life. Probably AP Bio talks about this as well. You can have these large molecules that have part of the molecule polar and part of it nonpolar. What's a really famous molecule that has a polar end and a nonpolar end? Oh, fat. Yeah, just want to get all the voices, different voices. Fat. So it has this large nonpolar tail and a polar head. So polar molecules be attracted to other polar molecules, and we'll come back to this later. This is going to form a foundation for one of our next chapters. But we have to understand, how can we tell if something is polar or not? All right. So, shapes. We're going to start with the Vesper theory. So this is an acronym for valence, shell, electron, pair, repulsion theory. Vesper is just a lot easier than saying that whole thing all at once. So what does this actually mean, though? So electron pairs, which can be either lone pairs or bonded pairs, will push each other away. So if we can figure out how many lone pairs and bonded pairs there are in a molecule, we know that they'll push each other away from each other. Wow, I said a lot of each other. They will push each other away. They will push each other apart. So, the Vesper theory. So the way I'm going to do this is I'll ask you, is it okay to move on? I don't want anybody saying no, right? Oh, wait. How am I going to do this? Crap. We will edit this out of the of the fun. So I'm going to ask you, do you, then, yeah, so, I never edited them out. Okay, so I will ask you, do you need me to wait? And I don't want anybody to say no, right? I just want people to say yes if they need me to wait, right? So that way we're only hearing yeses and nobody's saying no. Okay, so do you need me to wait? Okay. Perfect. I meant with this, I heard one yes, but it was confusing, so my instructions were obviously vague. So do you need me, are you all done with the notes? Okay. See, that was, I asked the question again as a yes. All right, so let's see if you can remember how to do the Lewis dot structure for CH4. So those of you watching at home should totally be proficient at this because you've watched the earlier parts of my lecture. Okay, so going around, most people have some good idea. I'm going to use purple. Whoops. Because that was the second color I heard shouted out. All right, CH4. So carbon is our central atom. In general, the atom that wants to bond the most goes in the middle, and then the hydrogens go around it. Now, this is a 2D model, right? If this were real life, each of these hydrogens would be separated by right angles of 90 degrees. Well, we don't live in a 2D world. So, what CH4, which is methane, what this actually looks like is what I have in my hand right here. All right. So, because of the valence shell electron pair repulsion theory, these bonded pairs, and if those who are watching at home are just pointing to the CH bonds, they want to push each other as far away from them. God, I need to figure out a better way to say that sentence. They want to push each other far apart. They want to maximize the space in between. Well, in a 2D world, 90 degrees is the maximum angle in between them. But if you go into the third dimension, you can actually create a structure where these bonded pairs are much more than 90 degrees apart. And what this actually looks like if you try to draw it in 2 dimensions is this. You have just kidding. You have your carbon, a hydrogen coming off here, a hydrogen coming off here. Now, we have to have some way of showing that we have 2 more hydrogens. In theory, you could just do this. But that doesn't really give you a 3D structure, right? It just looks like these 2 hydrogens are right next to each other. So the way we get around that, and we'll talk about this more momentarily, is we have ways to show things coming into and out of the board. So when I no longer have straight lines, I'm now showing you that I have some level of 3 dimensions to this molecule. Where this is called a wedge, and this is called a dash. So the 3 dimensions makes it possible to achieve angles greater than 90 degrees between the bonded pairs. Yeah. So the question was which one is which, and which one's in, which one's out. The wedge is out, the dash is in, but we're going to get to that. There's actually a couple slides about that in a little while. All right, does anybody need me to wait? Okay, good. All right, so electron pair geometry. We're going to start talking about our basic shapes in terms of how the electron pairs are arranged around a central atom. All right, so somebody shout out a color. All right, red. All right. Your key is start with the Lewis dot structure. Whenever you're trying to find out electron pair geometry or later molecular geometry, you're always going to start with your Lewis dot structure. And look at how electron pairs are arranged around the central atom. So I say central atom. Like in the case of methane, which I'm holding in my hand right now, the carbon is the central atom. But you can have these big, huge molecules, like things like as big as like proteins and DNA and stuff. When you talk about the electron pair geometry, you're just looking at, you make each individual atom look like your central atom while you're considering it. So you can have, all of the atoms can have an electron pair geometry. But we're just starting simple before we get into bigger molecules. All right. So this goes right to our previous question. If a bond is coming towards you, you draw the wedge, which is solid and just looks like a triangle. And if a bond is going away from you, it's the dash. And this is, what would we call that? Dashed? But dashed would imply like along the same lines, right? What do you call it? All right, so I guess dashed it is. Dashed. I actually have a hard time drawing this because I tend to make my lines all the same size. But really, when you draw the dashed bond, it should look like a triangle like the wedge, except just these little gaps in between. So if you imagine your molecule, and going back to methane, these two H's are actually blocking each other. If we were looking at this head on, the top H and the H on the left are on the plane with the board, right? And the wedge and the dash, the wedge is coming out, the dash is going in. But if you were looking at this straight on, you'd only see the wedge, you wouldn't see the dash, right? They're blocking, the wedge is blocking the dash. But we don't show that, right? We want to make sure that we know that there are 4 H's there, not just 3. All right, does anybody need me to wait? Okay, so we need to find our electron pair geometry, we need to count our electron domains. So each lone pair or bond is an electron domain, a group of electrons that will repel others. Now, the trick to this is, since for a double or triple bond, all the electrons are pointed in the same direction, right? They're between the same, essentially they're between the same two atoms, so they're going the same way. A double and triple bond only counts as one electron domain. So it doesn't matter if you have a single, double, or triple bond. Each one of those instances are only one domain when you're counting. So at your tables, quickly count how many domains are there around C, N, and C. All right, I'm going to use the cards. Don't be afraid to make mistakes. We're just sort of learning this at the same time. I'm going to find people. Ah. Eric, how many domains are there in this? 3 domains in this molecule, CH2O. That's ugly, so I'm going to rewrite it as 3. Oh, so I have 2 Alex. Yeah, Alex R. Right here, right in front of me. How many in ammonia? 4. You got it. See, there are 4. There are 3 bonds and 1 lone pair. So there are 4 electron domains here. And then how about CO2, Cameron S? 2. Now, I made you learn the actual sort of definition of electron domains. Now I'm going to tell you an easier way to count it. Maybe. So, electron domains is equal to the sides of the central atom that are, I'm going to put it in quotes, covered. So see, for CH2O, the carbon, the left, the right, and the top are covered, but the bottom is empty. Left, right, top, 3 domains. Ammonia, the top is a lone pair. Left, right, and bottom are bonds, so all 4 sides are covered. CO2, just the left and the right are covered. So if you just look at how many sides are covered, it'll tell you how many domains there are. It gets a little trickier because we can go beyond 4, but that's you'll see that when we get to it. Okay, so I will show you some examples now. I'm going to ask you to draw some Lewis structures, and then tell me how many domains there are around the central atom. So draw those Lewis structures. You can talk to each other at your tables. This is not solitary work. All right. So I'm just going to put them up on the board. Let's see. You guys can check to see if you're right. Carbon is the central atom. It's the one that wants to bond the most. All right. Oops. Now, I heard some questions as I was walking around. Or I heard one question when I was walking around. Does it matter where I put the CLs or the H's? For us right now, no. No. So we're not going to worry about where we're going to put the CLs or the H's. Anywhere you put them. The only thing you needed to make sure is that all the lone pairs are represented on the CLs. Okay, so how many domains does this carbon have? 2. And how many does this carbon have? 4. All right, so for those of you who were in Chem 1, you definitely have not seen the ones that are about to come up. If you were in Honors Chem, you might have seen some of these. We're about to break the octet. Dun dun dun. Oh my God, breaking the octet. So, all right, try these Lewis structures, PF5 and SF6. Yeah. Hmm? All right. Instead of letting you guys sit and struggle with this forever, I do want to go back one slide. Now, if we look at CH2Cl2, its 3D shape, if we take into account the Vesper theory, would be this, right? Just like methane before it. And again, right now, we don't care where we put the H's or the Cl's. With each of these angles being approximately 109.5 degrees. I forgot that I wanted to show you this. If you have 2 domains, what is the maximum angle between those 2 domains? 180. Pardon, you're like, All right, so now we're going to expand our octets. And if somebody's really good with grammar, they can help me figure out what tense to use in this sentence, because I have not yet explained expanded octets, but by the time everybody who's not sitting in this room watches, I will have explained it. I will have had explained it at some point in the future. Later on today, I'm going to explain expanded octets, but if you're watching at home, you've already watched the lecture. So, yeah, crazy. All right. It's all right. So PF5. PF5. So because fluorine is very electronegative, it really wants to pull electrons away. Phosphorus not particularly electronegative, as I will have had explained. We get this. All right, so that is the Lewis structure for PF5. Now, if we want to maximize the angles between these using Vesper theory, well, that's pretty tricky. This is the trickiest one. So we'll start with how many domains are there? 5. And then SF6 is this. So many dots. All right. So how many sides of sulfur are covered? 6. So there are 6 domains here. So in order to determine your electron pair geometry, you need to count how many domains there are around the central atom. All right. So what does this look like? So I made it too big. All right. So with phosphorus in the middle, we have a fluorine coming off the top, fluorine going off the bottom. Oh, no. Oh, my gosh. I have no idea what that is. All right, fluorine. Now, the other 3 are trickier to place. They go, one goes here, off to the side. What's this angle right here then? What does it look like? 90, and it's all on the plane, so it actually is 90. But now you get your next 2 fluorines not on the plane. And so what you get with 5 domains, and why I think it's the trickiest, is because you actually have 2 angles to worry about. You have the 90 degrees here. You have 90 degrees here between the ones that we can see on this plane, but then you have 120 degrees between the fluorines that are perpendicular coming into and out of the board. All the ones that are flat are 120 degrees apart, but the top and bottom are 90 degrees from this little thing. And while you guys are copying that down, I'm going to see if I can find. There's definitely more than one 90-degree angle. So there are, if you want to count all the possible 90-degree angles, there are 6. One here. Sorry, one here, one here. So you can have 2 with all the fluorines that are on the plane. All right, so I'm going to try to find one of these momentarily. Oh, good. Here we go. All right, so talk to each other. What does SF6 look like while I'm trying to build this? What do you think it's going to look like? All right. Oh, I'm really psyched that there's a group in the back using pencils to try to figure it out. That actually is going to totally make my day. No, that's awesome. Yeah. Yes. Yes. Yep. Yep. Okay. So, for those of you at home, I highly recommend coming in and playing with the molecule kits. We give you paper to do that with, like some worksheets or whatever. So this is a 5-domain. This is we're gonna pretend the white ones are Fs, even though they're normally Hs. So we see F on top, F on the bottom, F to the right, your left, my right, all on the plane, like whatever we want to call this plane. We can see your right-hand side, we have an F going towards me and an F going towards you. So see, this angle here is 90 degrees everywhere. But if I flip it and rotate it 90 degrees, the angle between all the ones that were previously on the plane is 120. So that's how you maximize the distance between these in a 5-domain molecule. All right. That's why it's most confusing. What did you guys say for SF6? What does it look like? I see some good hand signals. Perfect. So in SF6, whoops, all of the domains are 90 degrees apart. So the way you would draw that is like this. So the ones coming into and out of the board really are flat, right? They would be flat coming into and out of the board. And all of the angles are 90 degrees. All right. And I'll see if I can try to find one of those while you guys are doing this. And we have a group at the table in front of me talking about the Kardashians. I don't want to hear this. I don't want to hear that is pretty hilarious. Okay. I hope that didn't get caught on mic. So here is SF6. So you can see everything, no matter what way you spin it around, all of the domains are 90 degrees apart from one another. And I'll have you guys just pass it around. And Ari had a nice little scream as I threw it towards him. Okay. So now we're going to give names to these electron pair geometries. So 2 domains. The angles between the domains are 180 degrees. So if I have something that's 180 degrees apart, what do we call that? A line. So this is linear. I didn't show you the 3-domain one. We'll get to. So what do I call it if I have 3 domains? Do we remember? So every year, I love this lecture because we have arguments about how to pronounce trigonal or trigonal. Okay, so we're going to ask dictionary.com to say it for us. Oh, I'll put it right up to the mic. I think I did this last year too, but you know what? I don't even remember what it said. I'm going to do it on a different computer, though. All right. So, guys, listen up. Listen up. Wait, let's take bets. Who thinks it's trigonal? And who thinks it's trigonal? All right. We are about to find out. Oh. Trigonal. All right. Oh, it's going to get better, too. We have another one coming up. All right. This is dictionary.com. I mean, this is Merriam-Webster or whatever it is. All right. The angles between them are 120 degrees. And I'm going to look the other way while gambling happened in the classroom. All right. So 4 domains is tetrahedral. We call it tetrahedral. Tetra means 4, so tetrahedral. 4 sides. And this is about 109.5 degrees. Now, 5. If we looked at 5, I know I'm good at lecturing. I don't know that I need that round of applause. All right. And now I don't know how to turn it off. All right. Thank you, Verizon. All right. Random ad that popped up. Okay, so 5. We call 5. 5 was tricky. Remember, it was 90 degrees and 120 degrees. So if you look at it, it's almost like we have two pyramids. So we call it trigonal. Now, is it bipyramidal or bipyramidal? So, who thinks it's bipyramidal? And who thinks it's bipyramidal? All right. I don't know if this one's in there. All right. Moment of truth. Oh. Oh, bipyramidal does not come up. Yeah, bipyramid. All right. Yeah, but all right. So bipyramid. All right. So we'll leave pyramidal up for debate. Okay, the last one. Last one has 8 sides instead of 4. I know it's got 6 domains, but if you draw it out, it has 2 pyramids with 4 sides each. So 8 is octahedral. So if you think about it, if you drew out, and I'm holding this up, I'm holding up the SF6. If you treated the top and the bottom as a pyramid, each pyramid would have 4 sides. So that's where we get the octahedral from. All right. So it's good to know these names. It's better to understand how they come about. Right? If on a test, I don't think we tend to not ask names, right? We give the option of there being names. We give the option of you naming it, but you could also draw it for us, and that's fine. So if you don't remember that this is trigonal bipyramid, then if you draw us what it actually looks like, that's okay. All right, now we jump to molecular geometry. Oh, okay. I'm going to jump ahead a slide. Your slide has all like the NH3, H2O, NO2 minus. Move to the next slide. I want to give notes. I put these out of order. So if you want to find molecular geometry, it's different than your electron pair geometry. Or I should say, it can be different from your electron pair geometry. So why is that? How can your molecular geometry, what your molecule actually looks like, and I put that in air quotes, be different from the geometry of the electron pairs around it? Well, so you, again, start with your Lewis dot structure. From your Lewis dot structure, you can determine your electron pair geometry. And then what you do is you remove lone pairs, leaving a shape. But be careful, because you don't really remove the lone pairs. You just ignore. You don't even ignore the presence. The lone pairs still repel. But if you were actually observing a molecule, you couldn't see those lone pairs. You could just see the atoms it was bonded to. So those lone pairs are still there, but you don't take them into account for the molecular geometry. You've already accounted for them in your electron pair geometry. So what does that mean? Do you guys need me to wait? All right. So now I go back to this one. What are my 3 molecules? NH3. So NH3, I'm going to assume we can quickly do the Lewis structure of this. Now, how many domains are there in NH3? 4. 4 sides are covered. 4 domains. So I know, and I'm going to shorten it, my electron pair geometry is tetrahedral. So I start with my nitrogen in the middle. And tetrahedral, well, tetrahedral looks like this, right? So that's what the tetrahedral shape looks like. One going in, one coming out, 2 on the plane, all about 109 degrees apart from each other. But one of these is going to be a lone pair. So now I just erase lone pair. And I have my molecular geometry. So you start with your electron pair geometry, you erase the lone pair, keeping the electron pair geometry, and it gives you your molecular geometry. Yes? Perfect question. The question was, do you move it so it has the shape of 3 domains? No, it still has the 4 electron pair geometry domain, because that lone pair is there. But when we're talking about the shape of the molecule, we don't observe, we don't physically, like, we can't see these anyway, but like we take them away, keeping the electron pair geometry, leaving behind the molecule. So this still has the tetrahedral electron pair geometry, but we have a different molecular geometry. So anybody know what this is called? I heard it. Pyramidal. So let's see what dictionary, or is it pyramidal? I think it's fun. It gives us something to talk about that's not just boring lecture. All right, here we go. Who thinks it's pyramidal? Who thinks it's pyramidal? I'm going with the latter. Pyramidal. So this is pyramidal. All right. So now let's go to one that I feel like you guys know already. Because in middle school, I think, most of you learn about water as like the Mickey Mouse shape, right? So, again. All right. This one has 4 domains still, right? Oxygen, 4 sides of it are covered, 2 with bonds, 2 with lone pairs. So the electron pair geometry is still tetrahedral. So I draw the O in the middle. Now this is going to look a little funky to you guys when I do it this way. But I'm going to erase my 2 lone pairs. Which ones do you think would be easiest to erase? The ones that are coming in and out of the board. So when I erase that, I still have my tetrahedral electron pair geometry, but my molecule doesn't look like a tetrahedral anymore. It looks bent. Right? So you're used to seeing this in a different way. You're used to seeing it like I'm showing right now. Like this, right? You're used to seeing water like this. It doesn't matter if it's with the 2 H's down or the 2 H's to the side or the 2 H's going into the board or the 2 H's coming out. As long as you understand that there's still that bond angle between them of slightly well, we'll get to why it's slightly less than 109.5. But we have a bent molecular geometry. All right, the last one was NO2 minus. All right. So, yeah, Alex. Yep. So the question is, why is water bent? Don't the H's want to be as far apart from each other as possible? So we're removing, and again I'm putting in quotes, the lone pairs, but the lone pairs still have an effect, right? So the lone pairs are still there, we just no longer visualize them. They're still pushing the bonds apart and the electron pairs apart. So it starts as that tetrahedral shape, and then we just pop off the lone pairs without moving anything else around. The forces are still there. Yes, perfect way to put it. The force is still there. All right, NO2. And I didn't do this Lewis dot structure out, so you guys do it at your tables with me while I figure it out. I should know it. Try the Lewis dot structure for NO2. 6, 12, 18. Oops. NO is radical. NO2 minus is not so radical. Yeah. Nope. All right. So you should have gotten, since all of you are experts at doing polyatomic ions, or will have had become experts at doing polyatomic ions, so you should get this structure. So N, how many domains? 3 around N. So we do our N in the middle, the 3 bonds about 120 degrees apart. I put an O on 2 of them. I erase the 3rd one. And what does that look like to you? Bent. But be careful. It's bent, but the angle here is very different from the angle in water. Because this electron pair geometry was trigonal planar. I had to think about that for a second. Trigonal planar, where the domains are 120 degrees apart. This was tetrahedral, where they're 109.5 degrees apart. So this angle is going to be approximate. It's a little less than 109.5, but we'll talk about that later. And this angle is about 120 degrees. So they're 2 bents, but they have different bond angles because of their electron pair geometry. Whew. All right. So